In the last video lecture, we considered the case where we had the spaceship moving from San Francisco to St. Louis to New York, and the observer in New York, where they actually saw the spaceship seemingly coming toward them at 4 times the speed of light, or even 9 times the speed of light. In other words, it was a case of apparent faster than light motion. Even though the way we set up, clearly the ship was not moving faster than light. It was moving at 0.6 C or 0.8 C or 0.9 C or whatever we chose. But putting the numbers together, it seemed like, just because of the way the flashes of light worked as it traveled across, and the observer in New York would see the flashes of light coming right after each other, such that the effect was to seem that the ship was moving faster than light. What we want to do in this video clip is actually see what happens when you have a ship that can move faster than light, or just something in general moving faster than light. Just like the last example, actually this is from Taylor and Wheeler's book on space-time physics, although it's a classic example. You can find it in many other places. I've modified it just a little bit as well to get at the salient points that we want to make here. And so the theme is cause and effect or vice versa. And so it gives the ending away just slightly, but let's set up the situation here. We've got a diagram, but here are the events that we're going to imagine occurring. We've got the good guys and the bad guys, and they don't like each other very much. But at a certain point, they sign a peace treaty. So in year 0, there's a peace treaty signed, and the negotiating team for the good guys then leaves the home planet of the bad guys. So they actually went to the home planet of the bad guys and negotiated the peace treaty and got it all set and everything signed. And then they left in their ship to go back home at a velocity of 0.6 times the speed of light. And turns out that in the meantime, after they have left, over the next 4 years, okay, so we're calling that year 0. Over the next 4 years, the bad guys are able to invent a faster-than-light spaceship. And being bad guys, they say, we're going to take off in pursuit of the good guys, our enemies, because now we have a chance to really put it to them. And so they use their faster-than-light ship and take off at a velocity of 3 times the speed of light. And that happens in year 4. And then in year 5, they're able to catch up to the good guys, and they launch a sneak attack against them. So diagrammatically, on a space-time diagram, this is what it looks like. Okay, so this is the frame of reference of the bad guys for B here, for bad guys. It's in light years and years, so the velocity of light is 1 light year per year here. And the green line represents the negotiating team of the good guys taking off from the home planet of the bad guys, which is right here, and traveling back towards their home, wherever it might be. Now again, remember, they're actually not traveling at an angle. They're traveling along the x-axis here, going in this direction. But the space-time diagram shows their world line progress through time as well. So they'll space that way and then moving through time this way. And if the speed of light, again, is at a 45-degree angle here, this roughly is 0.6 C as we've drawn it. In other words, in 1 year, they go about 0.6 of a light year. In 2 years, they go about 1.2 of a light year, and so on and so forth. Not precise, but pretty close there in terms of the units involved and the scale involved. So they're traveling along here, going back home, really traveling along here, of course. This is their world line at 0.6 C. And then in year 4, the bad guys invent their faster-than-light spaceship. And at that point, they take off from their home planet. So they've just been sitting on their home planet here as time goes on, 1 year, 2 years, 3 years, 4 years, trying to make this faster-than-light spaceship work. And they finally get to work in year 4. So they take off at a speed of 3 times the speed of light. And because the other ship is going 0.6 times the speed of light, if you work it out, they're able to catch up with them in 1 year. They go, essentially, in 1 year, from here to here, they're able to go 3 light years, because it's 3 times the speed of light. So 3 light years per year is what their speed is. And over 5 years then, the other ship goes 5 times 0.6 C, which again is 3 light years. Okay, so they both end up 3 light years away from the bad guy's planet there, and that's where the sneak attack occurs. And from the bad guy's perspective, that sneak attack occurs at x sub b equals 3, okay, 3 light years away. and a time of 5 years. Okay, ticking off from 0 here. And what we'd like to figure out is, what is the time and location of this attack in the good guys' frame of reference? Okay, where they assume they're on their ship, they actually see the home planet receding away from them, they consider themselves at rest, or can consider that. And let's just do the Lorentz transformation and see what we get here. So that's what we're doing here, where the difference in the two frames of reference is 0.6 c. And also note that from the good guy's perspective, the bad guy's planet is moving to the left in the negative x direction, so we use the minus sign version of the Lorentz transformation. So the x location of the sneak attack here is going to be gamma x sub b minus v t b, where we've got x sub b and t sub b here, 3 and 5. Gamma for 0.6 c turns out to be 1.25. So we just plug in the numbers. 1.25 for gamma, 3 for x sub b, the location in the bad guy frame where the sneak attack occurred, and the time where the sneak attack occurred in the bad guy frame. And we're transforming it now into the good guy's coordinates. And note what happens here. X sub b is 3, v is 0.6 c, really, but we're using unit c as 1, so we can just put 0.6 there. T sub b is 5, and therefore 5 times 0.6 is 3. We get 3 minus 3, we get 0 there. You say, well, does that make sense? Well, think about it a minute. From the perspective of the good guy's ship, the sneak attack occurs right at their ship. That's their 0 point, right? That's the 0, the origin in their frame of reference. So yes, it does make sense that they get x sub g equals 0. It occurs right at their ship, which again is their origin point for their frame of reference. Now, what about the time, though, where they see that occur? So again, we plug in the numbers. Equation gamma t sub b minus v over c squared x sub b, of course, again with the minus sign, because from the good guys, the planet, the bad guy frame of reference is moving to the left, negative x direction. And plug in the numbers, you get a 5 minus 0.6 over c squared. Again, c is 1, so that just becomes 1 times 3. So if this is 3 times 0.6 is 1.8. 5 minus 1.8 is, 3.2. Multiply that by 1.25, and you get 4 years. Okay? So that in the good guy's frame of reference, which we're not showing on this plot, we could put it on here, but we're not going to get it too complicated in terms of the plot that's going on. But we see their clocks read 4 years at that point. And really that makes sense because you just have a time dilation effect going on here between the bad guy's clocks, which tick off 5 years, but from the bad guy's perspective, the good guy's clocks are running slow, and so they'll tick off 4 years, assuming they both had their 0 point for their clocks when the good guys left the planet there. Okay, so nothing too amazing there or confusing, just in case of however confusing it might be in terms of time dilation and things like that. But nothing that is overly surprising there. Now, however, let's ask the question, what is the time of the invention of the faster-than-light ship and the launch of that ship in the good guy frame? Okay, so that's this point right here. In the bad guy frame, they launch their ship. Put a black mark there to indicate that's the launch of the ship, the bad guy's launch of invention of the ship and the launch of the faster-than-light ship. What time does that occur in the good guy's frame? We know the sneak attack occurred 4 years in their frame. Let's see what this does. Same equation again. We'll actually just do it over here. So we have, in this case, T sub g equals gamma times T sub b minus v over c squared x sub b. And for the invention and launch right here, notice that, we can put gamma in first. We'll do that. So it's 1.25. What time does that occur in the bad guy's frame? Well, it occurs at t equals 4, right? That's the time that occurs, so it's 4. And then minus 0.6 over c squared. And where does that launch occur in the bad guy's frame? The x sub b coordinate? It's just at 0. It's on their home planet, right? So that's the 0 point in their coordinate system. So actually, this whole thing, the second thing here, is just times 0. Okay, so that whole second term disappears, and I'm just left with 4 in the middle here. It's 4 minus 0. And 4 times 1.25 is 5, and our units are years. So, look what we've got here. In the good guy frame, the invention and launch of the spaceship occurs at 5 years, according to their clocks, and the sneak attack occurs at 4 years. In other words, the sneak attack occurred in their frame before the ship was even invented. So how can you have that? I mean, in other words, it reverses cause and effect. Okay, normally cause happens, and then you get the effect. Here you have the effect happening before the cause. And since, as far as we know, that never happens, if things like that did happen, science would almost be impossible, because you never know whether you're talking about cause and effect and what the order of events was and so on and so forth. So this is another indication that things cannot move faster than light. Because if something, either a material object or also even a signal bearing information, if it could move faster than light, then you can have situations like this where the effect happens before the cause. And again, what we see here is a sneak attack by our Lorentz transformation calculation occurred at 4 years, according to the good guys' clocks. And at that point, according to their clocks, the ship that just attacked them hadn't even been invented yet and hadn't been launched yet, because that's only going to occur in year 5 in their system of clocks. And so you get a very deep contradiction here. And so given this, we'd say, nuh-uh, you can't have anything moving faster than the speed of light, at least when you talk about material objects. As we mentioned before, there are somewhat esoteric theories where people have tried to imagine, what if you could have these things called tachyons, which would be particles that could move faster than the speed of light. People worked with those for a while. It didn't seem to really get anywhere. They weren't able to do anything with it that was consistent, and so had pretty much given up on that. Doesn't mean it's not impossible necessarily. Might come up with a new theory or just new experimental evidence, but certainly in terms of cause and effect, we've never seen that sort of thing violated. Somebody may be thinking, well, what about quantum mechanics, quantum physics, all the weird stuff going on there? If you analyze it carefully, you don't get violations of the special theory of relativity. There are other weird things going on there, but special theory of relativity seems to hold up. Again, doesn't mean that people aren't thinking about it in ways that might not be satisfied, or we could go beyond it. And occasionally, every once in a while, experimental evidence comes up that seems to suggest maybe something is going faster than the speed of light, although so far, in every case, further analysis has shown, no, the analysis wasn't quite correct, or there are some mitigating factors, confounding factors that made the special theory of relativity still hold true.